Hello everyone, welcome to this chemical kinetics discussion, and in this video we are going to be looking at how we can use a simulation software or platform. Preferably we are going to be using Python to discuss this question and provide a solution for it. So the question says, in a laboratory experiment, the composition of hydrogen peroxide, H₂O₂, is being studied. The initial concentration of hydrogen peroxide is 1.0 moles per liter. That's the molality of hydrogen peroxide. And the rate constant K, for the reaction is found to be 0.1 liters per mole per second. The reaction follows second-order kinetics with respect to hydrogen peroxide. Question: how long will it take for the concentration of hydrogen peroxide to decrease to 0.25 moles per liter? So here we are going to be looking at, first of all, the reaction where hydrogen peroxide is decomposing into oxygen and water, and then after doing that reaction, of course, this is the equation, then we come and apply the rate laws. Of course, this is now the process of modeling or coming up with a model that is going to help us answer this question. So we start with the chemical equation, which is hydrogen peroxide decomposing into water and oxygen. Then the rate laws that we are going to be considering, obviously, this is just a discussion of all the rate laws, but we are supposed to be using second order. So for zeroth order, the rate is equal to K. For first order reaction, the rate is equal to K times the concentration of A. Then the rate is directly proportional to the concentration of the reactant. That's the statement. Then the one that we are supposed to use is that the second order reaction, where the rate is directly proportional to the square of the concentration of the reactant. And then when we go through by using the second order, obviously, here A is going to be representing hydrogen peroxide. So let's rush and look at, if we are going to look at the model, so we have adopted the second order reaction. So rate is going to be K times the square of concentration. But we know that the rate is negative D, or change in reactants divided by change in time. So here, rate is the same as change in what? In reactants over change in time. Why are we putting a negative? It's because as time goes by, the reactants are changing. In other words, the amount or the quantity of hydrogen peroxide is decreasing. Therefore, if we substitute in the reactant being A, remember we said A is hydrogen peroxide, so this becomes the equation. But now, remember our rate law. Our rate law says that the rate for a second order reaction is directly proportional to the square of the concentration. So if I call that equation 1, I call this equation 2. From 1 and 2, I see that negative D, the concentration of A by dt, is equal to K, concentration of A squared. So if I use separation of variables, I'll find myself introducing integrals. This is just a solution, how we solve ordinary differential equations, a simple case. So we find that we have 1 out of concentration of A equals a constant plus the rate constant K times T. So when we apply in the initial conditions, we find that T is equal to 0. So when T is equal to 0, the concentration is going to take a subscript to O to represent the concentration of hydrogen peroxide at time is equal to 0. Now, if we substitute in those values, we find this one is 0. So we remain with the C equal to 1 out of the concentration of A at T is equal to 0. So if I bring it back to this equation here, what I will get is 1 out of the concentration of A is going to be the concentration. This is instantaneous concentration at any one point, at any time t. The concentration of hydrogen peroxide or A is going to be 1 out of concentration of A. We are saying that the equation is going to be 1 out of the concentration of A equal to 1 out of concentration of A at t is equal to 0 plus kT. So what does that mean? Now, if we, having obtained our law, we know that these values are given to us from the scenario. We are given that originally, from the statement here, from the question, originally, the concentration or the molarity of hydrogen peroxide is 0.1. It is actually 1.0, then rate constant is 0.1, and then we want to determine the time for which the concentration will have gone to 0.25 moles per liter. So we are putting our information here, and so if we arrange the equation, the model that we just obtained, we are able to get T equal to 1 out of the concentration of A minus 1 out of the concentration of A at T is equal to 0 divided by the rate constant. So if we know these values, we are able to determine T. So right away, let's go to Python and do the solution or the coding of this problem. So I'm going to be using VS Code or Visual Studio Code. And then for me to simplify the things and to spend less time, I've already made a frame of this code. I'm just going to be feeding in the information that we have so that we run this, this model and see the outcome. So first of all, in Python, you have to import the libraries that are important. This is NumPy, which is a numerical Python that helps you to manipulate data, helps you to do the plotting, it helps you to, visualize your data. Then the Matplotlib is now another library that is helping you to actually do the plotting. So we shall say import NumPy as np, then import Matplotlib for plotting, .pyplot as plt, and then we continue. So now we are going to be defining the model that we are going to use. So the model, remember, is a function that is going to be for second order, and this function has 3 inputs. Remember, we have the concentration of A when the time is equal to 0. Then we have the concentration we have the rate constant and we have time. So let's put in, obviously we are talking about this equation that we just derived. This is the equation that we're talking about. We need the inputs to this model. We need this concentration at T is equal to 0. We need the K, we need the time. So let's go back. So now this model is going to be, we are going to say it's concentration. We are going to call it A. Remember, we are supposed to call it hydrogen peroxide, but for simplicity and to make our code look unclouded, we are going to be using A. So concentration, comma, we said we need the K, we need the time. So that is, those are the inputs to our model, and therefore we are using this method define, which is a function, which is helping us to define our function or create a function. Then we are going to be saying that this concentration of A, of course, we need to define it. So we are going to put it down here, and this is going to be what? This is going to be concentration of A at any one point is going to be 1 divided by 1 divided by the concentration at 0, then plus K times time. So we are going to bring this. We are putting it here, okay? So what we are doing, if I do this, if I want to get this concentration of A, I'll just bring this, I put it under 1. So the concentration of A will be on this other side, and 1 will be divided by the whole of this. So what we are going to do is that this is going to be 1 now divided by 1 divided by concentration of A, okay? Concentration of A at T is equal to 0. Then we are adding there our K times time. So what will this function return? This function is going to be returning the concentration of A. So let's put that. So it is going to be returning the concentration of A. So we proceed. Now, the parameters have to be initialized. So this is the initial concentration of A at T is equal to 0. Then K, the rate constant, is 0.1, has been given. Then we need to do to write down an array of time so that we remember this is going to be an input to this model. So time is one of the dependents. So each value of time will give us an output of the concentration of A. Therefore, we are creating an array of time ranging from, we are creating data points equivalent 500, ranging from 0 to 50. Okay, then we are going to write down the concentration of A over time. So how is it going to be? Remember, we created a function called the second order reaction. So we are going to rewrite it down here. So we are going to say second order reaction. What are the inputs? We have concentration of A at T is equal to 0, then rate constant K, and time. So let's go to plotting. So we are going to have a plot where we have X on the X-axis, we have on the Y-axis. And on the X-axis, we are going to be having time, and on the Y-axis, we are going to be having the concentration of A. So what we are going to do here is we are going to say the function that we use for plotting on the X-axis is PLT dot. Actually, we are going to label the axis. So X label. This is going to be a string. Remember, so in a string, that is how we declare a string in Python. Okay, when we are talking about label, so we are saying this is supposed to be time. It's going to be time in seconds. Okay, then we need also PLT dot Y label, so that we label the Y-axis, and this is going to be concentration of A. Remember, we can let's just copy this, put it here. It's going to be concentration of A. Units is in moles per liter. Remember that. So moles per liter, and then that's done. Then the title is going to be, we are going to call it second order reaction. So legend, we shall declare that let there be a legend. In other words, like something like a key. Then let the grid be there. This is how we declare that let there be the grids. We use PLT.grid is true. If you don't want, you can say false. But even if you don't put it, as long as you have not declared it, it is going to come when it is praying. Then PLT.show is what is going to help us to show the output. Now, we need to look at the question that has been asked us. The question was like, how long will it take for the concentration of hydrogen peroxide to decrease to 0.25 moles per liter? So what we are doing here is now to initialize. Let the concentration of A be 0.25. And the time for reaching 0.25, we are going to use a model that obviously we derived, and this model is here. So we have T is equal to 1 out of concentration of A minus 1 out of concentration of A at T is equal to 0 divided by rate constant. So let's write that. We are going to say time for that is going to be, we create a bracket, it's going to be 1 divided by the whole of the other expression. So this is going to be, okay, no, not the whole expression, but it's going to be 1 out of A, 1 out of A, then minus. We are taking away 1 divided by concentration. Remember we had the concentration at time is equal to 0. So remember it's also part of the equation. So we divide the whole thing by K. So the moment we do that, we want to print the results in our terminal so that we are able to see what is that time going to be. So we are going to use the formatted string literal F string in Python, and it is going to help us print out a string that has that involves also a value that we have earlier on calculated. For example, if we are formatting our output like time for concentration to decrease to 0.25 moles per liter is going to be whatever it is going to be, it's what is going to be here. And that is going to be the time that will be computed from this function. So we copy this variable and put it here, and then it will be in seconds. So finally, it's time for us to try to run our program and see. So let's run. Okay, wow, this is beautiful. Our program has run successfully, and you can see that the concentration is on the y-axis and time is on the x-axis with the values ranging from 0 to 50. And you can see that originally the concentration was at 1.0 moles per liter, and it keeps on reducing. So the time for which the concentration will be at 0.25, remember, 0.25. So let's close this and see the value here. So we had K somewhere. Our K must be defined properly. So this is K, which should be in small. So let's run again. So you can see whenever you have any error, the system will show you. So let's close this and see the output. So you can see that the time for the concentration to decrease to 0.25 moles per liter is 30 seconds. So here, this is the answer that they wanted, and we have found it using a computer simulation. And if you are a chemist, an industrial chemist, a chemistry enthusiast, remember, this is a basic example, but you can do more and complex simulations that can help you to, of course, using computer software, for example, search Python, you'll be able to answer complex questions, or you provide the solutions to complex problems. Thank you so much. See you in the next video.